Sir, I have some doubts. Sir,
Please.
can you tell me the significance of delta H naught?
Delta H naught is the heat of reaction which is calculated at reference temperature, which is 298. So, you can write either delta H naught, or you can also write delta H 298. It simply says that this heat of reaction is calculated at the reference temperature, which is in all thermodynamic calculation is taken as 25 degrees Celsius or 298 Kelvin.
Sir, is it necessary to include latent heats in calculation of delta H while calculating at melting or boiling points of material?
It depends. Now, suppose I give an example. Suppose you want to calculate the heat content. For example, I take metal which is solid at 298 Kelvin, and I want to calculate heat content, for example, metal which is also solid at melting point. This is one situation, and another situation I take metal which is solid at melting point, and that is equal to m liquid at melting point. I hope this is your question. Now, you want, suppose if I calculate, or if I want to calculate heat content in the first case, then definitely latent heat will not be included, because the metal is metal or material or any compound that is not melting. It is simply solid at the melting point. So, there you do not need to include the latent heat. Similar is the case of latent heat of vaporization, whichever the case may be. Whereas, in the second case, where the metal at the melting point is transferring into metal at liquid at the melting point, so there you have to consider the latent heat of melting or latent heat of vaporization if ml at melting point is transferring to ml at the vapor. Because, and you should also know, or you should also note, that when the liquid melts, temperature does not change. That is what in fact the latent heat means. And the, say, if you consider the term latent heat, it is the heat which is latent, which is formed or which is because of the disruption of the bonds in the solid and making everything free in the liquid. So, at that transformation, the temperature does not change. That is the important thing. Is that okay?
Sir, will heat of formation be different when calculated from different compounds or from pure elements?
Yes. Say, if you just imagine, say you are forming a compound using pure elements. Let us take any example. For example, you want to form say calcium carbonate. Calcium carbonate you can form by using calcium, carbon and oxygen. Then definitely you will require very large amount of heat as when you form from calcium oxide and CO2. This I can illustrate again by giving an example. For example, I take an example of calcium carbonate. So, let us form say calcium carbonate CaC3O. This has heat of formation minus 289 500 kilocalorie. This is delta H naught F, heat of formation when calcium carbonate forms from Ca, C and 3O. Now, again I take element. For example, I take now calcium and oxygen that has heat of formation minus 151 6000 kilocalories, and then CO2 that will be equal to minus 94,400 and 450 calories. Now, your question is, for example, if I want to form calcium carbonate by using CO and CO2, will the heat of formation same or different? So, now let us see. So, if I form say Ca plus C plus 3O, that is equal to Ca CO3, where delta H naught F is minus 289 500. Let me write down again, minus 289 500 kilocalorie, right. Now, let me form it as Ca plus O, that is equal to CaO, and delta H naught F, that is equal to minus 151 6000. Similarly, then C plus O2, CO2, and here it is minus 94,450. Now, if I subtract, say if I take this equation 1, this is H2 and this is H3. Now, if I use equation 2 and 3 and 1, 2 and 3 all together and try to form an equation which is say CaO plus CO2, then I calculate by subtraction, and this heat of formation for the formation of calcium carbonate, that will be equal to 43,450 kilocalories. So, you note that when calcium carbonate forms from compounds like CaO and CO2, then heat of formation is much less as compared to when it forms from the pure elements. So, that is what the case. I will illustrate this thing one more while taking the example.
Sir, can you derive the formula of heat of reaction at high temperature using delta Cp?
Yes. Now, for that you have to use, let me illustrate, say taking an example. Let us take an example, say AA plus BB, that is equal to CC plus DD, where small b, small c and small t are the moles of the respective reactants and product. Now, if I want to find out delta HR at temperature T, which is other than 298 Kelvin, then this will be equal to delta H naught 298 plus summation of HT2 minus H298 of all products minus HT2 minus H298 all reactants. That is what the thing. Now, we can calculate, say for example, I want to calculate now, I can calculate HT2 minus H298. Now, this HT2 minus H298 I have to calculate for all the products as well as for all the reactants. So, if I calculate, so if I see on the product side, I have C into C plus D into D. So, HT2 minus H298 for each product I have to calculate. So, for example, if this is, if I take say for all product, then this will be equal to C moles 298 to T2 CPC dt plus 298 T2 CPD dt. Now, this is the which is one? Right, sorry. So, it has to multiply by the moles, say D into D. So, this has become now the heat content in the product. Now, let us calculate, similarly I can calculate for reactant also. So, HT2 minus H298 for all reactants, that will be equal to A 298 to T2 Cp A dt plus 298 to multiply by the moles to T2 Cpb into dt. or then I can also calculate delta Cp. Now, delta Cp will be equal to C Cpc plus D Cpd minus A Cpa plus B Cpb. Now, then delta Hr, that is equal to delta H not 298. Well, if you write 298 or not, but once you put the superscript as not, that means it is at the reference temperature. Delta H naught 298 plus 298 to T2 delta Cp into dt. So, that is how you can evaluate the heat content at temperature other than 298 Kelvin. You can evaluate this way also, or whatever I said in the lecture, that way also. Is it all right? Okay. Any other question?
No, sir.
Thank you. So, now when there is no question, then I proceed on the solution of the problem. So, first of all, what will I do? I will give you the problems, and then I will follow the solution one by one. So, here are some of the questions. Question 1, carbothermic reduction is commonly used to produce metals from oxides. Now, in pyrometallurgical extraction, reduction of oxide is commonly done to produce liquid metal. The typical example is that of iron making, where Fe2O3 is reduced by carbon. Another example is production of zinc by using carbon, simply because carbon is abundantly available and it is cheap. That is, economics works better while producing metal using carbon as a reductant. Calculate the heat required in kilocalorie per kg of zinc. Remember, I did not ask kilocalorie per kg mole, but per kg of zinc to produce zinc from reduction of ZNO with carbon. The reactants ZNO and carbon enter at 25 degrees Celsius, whereas zinc vapor and CO gas leave at 1027 degrees Celsius. Now, remember, here zinc is produced in the form of vapor, not as a liquid. Use the following data: Zn S to Zn liquid, melting point is given, latent heat is given, and similarly zinc liquid, zinc gas, boiling point Tb stands for boiling point, Tb stands for boiling point, which is 11 atk, and latent heat of vaporization is given, which is that is. Now, here again, remember, to simplify the problem, we have given you the values of heat of formation of the oxides as well as Cp values. In fact, while proceeding any thermodynamic calculation, one has to do very careful search about the data, what data you needed to calculate the problem. Now, for example, if I had stopped by not giving the data, then probably you have to think that what data you will need to solve the problem. But for simplification, I have given all the data which will be required for solution of the problem. Normally, when you perform heat balance in any unknown situation, then you have to think what data you will need, and that is a very, very important exercise in calculation or in the thermodynamic calculation. So, here ZNO, carbon, zinc, CO, Zn and all the given heat of formation, then Cp values are given. This is the problem number 1. Problem 2, calculate heat of formation at 1250 Kelvin for the following reaction: zinc sulphide plus CaO plus carbon, zinc gas plus calcium sulphide solid plus CO gas. Here again, zinc liquid, zinc solid to zinc liquid, melting point is given, and zinc liquid to zinc gas. Here, instead of melting point, it is the boiling point, and Tb is the boiling point. Tb, that is equal to boiling point. Where Tm, let me be more clear, that is equal to melting point. So, here again all the data are given. Now, here you have to find out the heat of formation at 1250 Kelvin. I have just now explained how to calculate, and here there is a problem to calculate the heat of reaction. Various values of Cp are given and the data are with you. Let us go to the problem 3. Problem 3 says an electric furnace is used to melt copper scrap. Now, this particular problem tells you the straightaway application of the calculation of the heat of reaction for say production purposes. So, this problem is based on this. An electric furnace is used to melt copper scrap. The scrap is initially at 25 degrees Celsius. The overall power consumption is 300 kilowatt hour per ton of molten copper when heated to a temperature of 1523 Kelvin. Now, here copper is heated from 298 Kelvin to 1523 Kelvin, and it is in that process of heating from 298 Kelvin to 1523 Kelvin, the power consumption is 300 kilowatt hour per ton. Estimate the thermal efficiency of the furnace. The data are again given. Melting point of copper 1356. So, you must be noting from here that you are heating to a high temperature 1523. So, you will be needing first of all the melting point of copper. Well, naturally that you need, but then you should also think, in the absence of this data, you should also think that you would require the latent heat of melting, as well as you also require the Cp value of liquid copper, because that is an important thing. I mean, you should know what values you need before you begin to calculate. Now, here we have given all the values, but then in unknown problem again I am stressing this is the main issue. In various thermodynamic calculation, many times you do not get the data, you have to estimate the data, you have to search the data. So, that is an important thing. So, Cp and everything is given. Now, fourth problem, given the following heats of formation in calorie per gram mole, CaO, this one, CaSiO3, CSiO2 is given to you. Write each of these in the form of a thermochemical equation. From these equations, determine the heat of formation of calcium oxide per kilogram of calcium. Let's take the next problem. Given the following heats of formation, FeO, SO3, FeSO4, required the molar heat of formation of FeSO4 from FeO and SO3. Now, here you must have noted that this problem is just now I had explained about the calculation of calcium carbonate. So, this is another problem is for calculating this molar heat when FeSO4 from two different compounds. Sixth, calculate heat of reaction for production of silicon carbide. The reactants and products are at 1973 Kelvin. Again the values are given and you should calculate. 7, an electric furnace is used to produce calcium carbide as for the following reaction. Power consumption is given. The calcium carbide reacts with H2O according to the reaction, this one. Here the thermodynamic values are given. Say you have heat of formation of calcium carbide, calcium carbon monoxide and calcium oxide. Mean heat capacity of cold water is given. So, you have to answer the minimum power to produce 1 ton of calcium carbide, the electrothermal efficiency, and if 200 gram of calcium carbide is treated with 20 kg of cold water, no 20 kg, not 20 gram, calculate the rise in temperature. And the last problem, calculate the heat of reaction Al2O3 plus 3C, that is equal to 2L plus 3CO. Now, before this I have to tell little bit about this reaction. Now, what happens in the Hall-Héroult cell, the electrolysis of Al2O3 is done. Al2O3 has a very high melting point, and therefore, to bring Al2O3 in the liquid form, a cryolite is used, and at that with the in presence of cryolite, the Al2O3 dissolves at a very low temperature. Otherwise, the melting point of Al2O3 is 2,500 degrees Celsius. So, when cryolite is used, then Al2O3 dissolves at around 1000 degrees Celsius, and electrolysis is possible. So, this problem addresses to the electrolysis of aluminum. Just a short introduction about the electrolysis of aluminum. So, calculate the heat of reaction taking place in the Hall-Héroult cell at a temperature of 1000 degrees Celsius. Although this temperature is below the melting point of Al23, I have said the melting point of Al23 2500 degrees Celsius, the alumina is actually in the liquid state being dissolved in molten cryolite because it forms a compound. So, Al23 it dissolves into the cryolite bath. Assume therefore that the heat content of the Al2O3 includes its heat of fusion. So, heat of fusion of Al2O3 and melting point of aluminum is given, then you have to find out the heat of reaction of this reaction. So, let us proceed now for the solution of the problem. Now, in fact, I wanted to hide this slide before I go for the solution, but you are fortunate enough that the slide contains the answer and I have projected the slide before I proceeded to the solution. But I hope that you will not see the solution and you will follow, you will do the problem first and then see the solution. So, I proceed the solution to the problem one by one. So, here we go for the solution to the problem 1, say ZnO solid plus carbon solid, that is equal to zinc gas plus carbon monoxide gas. Now, here it is given reactants, they are at 298 Kelvin, reactants are at 298 Kelvin and the products at 1300 Kelvin, that is given to us. So, now we have to find out the heat of reaction, we have to find out heat of reaction at 1300 Kelvin. So, as usual you know that heat of reaction are at, for example, 1300 Kelvin, that will be equal to delta H naught 298 Kelvin plus H 1300 minus H 298 product minus H 1300 minus H 298 reactant. Now, mind you, because the reactants are at 298 Kelvin, so therefore, this term gets ruled out and this will be equal to 0 in this present case. So, delta H 1300 will be simply delta H naught 298 plus you have to evaluate the heat content in the product, that is all. So, delta H naught 298 you can evaluate from the data which is given, that is equal to 57,380 calorie per gram mole. You please do this exercise and try to get a practice how to calculate delta H naught 298. Now, as I said, since the reactants are at 298, so sigma HR that is equal to 0. So, now we have to calculate say that of the product. So, delta H Zn at 1300 Kelvin, that will be equal to, now here you have to be careful to integrate from one temperature to another, say in the state in which the zinc is. So, 298 first of all you go up to the melting point, that is 692.5. So, you will use the Cp of solid zinc 5.35 plus 2.40 into 10 to the power minus 3 T dt. Now, next step would be what? Next step will be you have to add the latent heat of melting, do not forget, that is 1740. What will be them next? Then next, then you have to also add the heat content from liquid zinc to the boiling point of the zinc, that is plus 7.5 is the specific heat of liquid copper into 1180 minus 692.5 plus what will you do now? You have to add latent heat of vaporization because again there is a transformation. So, latent heat of vaporization is given 27,565. Still your heat content is not yet complete at the temperature which is given in the problem, because so far you have reached up to only the vapor state. Now, vapors are further heated up to 1300. So, you have to add it plus 5 into 1300 minus 1180. So, that makes the heat content in zinc vapor at 1300. In fact, what I have done that zinc at 298, you have to do zinc vapor at 1300 Kelvin. You can also subdivide this step, say zinc 298 to zinc melting point 692.5. Should I do for that? You can also do this way, say zinc at 298, it will go to zinc 692.5 at melting point. This is the solid and this is also solid. Now, zinc solid at 692.5, that will go to zinc liquid, zinc solid will go to zinc liquid again at temperature 692.5, then zinc liquid at 692.5, it will go to zinc liquid at 1180, heat content will come, then zinc liquid at 1180, that will go to zinc vapor at 1180, and then zinc vapor at 1180, that will go to zinc vapor at 1300. So, you can also divide the sub steps. Probably in the beginning it is good that if you divide these in sub steps and then you proceed to calculate. Now, again we have to calculate the delta HCO. We have calculated only Zn. So, delta HCO say again at 1300, that is what we have to calculate, that will be equal to 298 1300 CPdt. You can use the values which I have given, and the value will be coming out to be equal to 7560 calorie per gram mole. So, delta HR 1300 Kelvin, that will be equal to 157380 plus 36141 plus 7560, that will be equal to 101,081 calorie per gram mole. Now, since the question says you have to calculate kilocalorie per kg of zinc, so all that you have to use the atomic weight of zinc, and I write down, say atomic weight of zinc is 65. So, for the answer, that will be equal to 1555.1 kilocalorie per kg zinc. So, that will be the answer for this particular problem. I hope you must have understood this particular problem. Now, let us do the problem number 2. Let us do the problem number 2, and problem number 2 says that you have to calculate the heat for the following reaction ZnS solid plus calcium oxide solid plus carbon solid, zinc vapor state plus calcium sulphide solid plus carbon monoxide gas. So, same thing you can calculate, I am straight away giving the delta H naught 298, that value will be 63,380 calorie per gram mole. So, this problem I think I will leave on you so that you can do it. So, here what will I do? I am simply writing down the answer, which is delta H R at 1250, that is what you have to calculate. It is coming out to 91,206 calorie per gram mole. This is the, because I had done the problem 1, so problem 2 is similar. All that you have to calculate the heat of summation of the heat of product and heat of reactant, and then you can proceed yourself. So, problem number 3, in the problem number 3, in order to calculate the efficiency, what you have to do? You have to find out the heat of reaction. You have to find out heat of reaction at 1523 Kelvin. So, if you find out the heat of reaction at 1523, then you can calculate power required theoretically because you have calculated the heat of reaction. So, only that much power will be required. So, power required theoretically, that will be equal to 47,658 upon 63.5, whereas here 47,658 is the delta H R at 1523. You can put delta H R at 1523, that is in joule per gram mole. 63.5 is atomic weight of copper. So, this will come out to be equal to 208.5 kilowatt hour per ton of copper. I have done this conversion in my lecture on units and dimensions, so please follow it. So, the efficiency would be efficiency would be 208.5 upon 300 into 100. So, efficiency will be 69.5%. That is the answer for the problem number 3. So, problem number 4, it is very simple problem, only you have to write down the equation. Maybe I write down, say the equation will be CaO plus SiO2, that equal to Ca SiO3. Let us take this equation number 1, and here delta H is given to be equal to minus 25,200 calorie per gram mole. Another thermochemical equation would be calcium plus Si plus 3O, that will be equal to Ca SiO3. Let us take it, equation number 2. So, delta H, that is equal to minus 377,900 calorie per gram mole, and the third equation would be Si plus 2O, that is equal to SiO2, and delta H, that is equal to minus 201 calorie per gram mole. So, this is the part where you have to write down in the form of a thermochemical equation, and from this equation determine the heat of formation of calcium oxide per kilogram of calcium. So, subtract equation 1 and 3 from 2. Let me put this equation as 3. So, if we do that, all that from these equations we have to build an equation which gives us the formation of calcium oxide, that is what it means. So, we build the equation Ca plus O, that is equal to CaO, and delta H for this reaction, that will be equal to minus 377900 plus 201,000 plus 25,200. So, that will be equal to minus 151,700 calorie per gram mole. So, if I divide it here by the molecular weight of calcium, which is 40. So, if I divide this minus 151,000 divide by 40, then I will get the answer would be minus 3.8 into 10 to the power 3 kilocalorie per kilogram of calcium. So, that is the answer for the problem number 4. Now, about the problem number 5th, I will straight away give the answer because the similar problem I have done in the problem number 4. So, I am writing down the though answer I had already given, but still let me put it. So, the answer for this problem, that is 63.1 kilocalorie per gram mole. Now, let us go to the solution of problem number 6th, which says that you have to find out the heat of reaction for the production of silicon carbide. So, here the reactants and product both are at 1973 Kelvin and the various values are given to you. So, let us take it the reaction, say SiO2 plus 3C, that is equal to SiC plus 2CO. From the data I can find out delta H naught 298, that will be equal to 499,474 joule per gram mole. Then I can calculate now delta H 1973. Again I write down the reaction for you, that is delta H naught 298 plus H 1973 minus H 298 product minus H 1973 minus H 928 reactant. So, you calculate, I am straight away writing down the value of the answer is 565.945 kilojoule per gram mole. So, that is the answer for problem 6. Now, similarly for problem 7th, this electric furnace is used to produce calcium carbide and so on. So, minimum power you have to calculate, efficiency you have to calculate. Now, for example, if I take it now again, say CaO plus 3C, that is equal to CO plus calcium carbide. So, I have to calculate heat of reaction. I am straight away calculating for you. the data are given. So, heat of reaction that will be equal to 1721.25 kilocalorie per kg of calcium carbide. So, I will give the answer now. Power required, A, you have to convert it now. So, the power required, that will come 2001.4 kilowatt hour per ton of calcium carbide. P will efficiency, straight away you can find out 2001.4 upon 4000 into 100, that is equal to 50%. And for the C part, you have to calculate. I leave it on you to calculate, and the rise in temperature that I am getting is 4.3 degrees Celsius. So, this I am leaving on you to calculate the rise in temperature. You have to do the heat balance, I mean, that you remember. Now, the problem 8th, which says you have to calculate the heat of reaction, because I have done so many problems on heat of reaction. So, what I will do is that I will straight away give the answer for this problem, though the answer for this problem is 1241911.3 joule per gram mole. So, this exercise and their solutions I have given to you. Now, I will like to give you the references from where you can see for further reading. So, the references, number 1, Y. K. Rao, stoichiometry, and thermodynamics of metallurgical processes. I will say this is a good book, and you should see also this book and read there from there. This is Cambridge University. London, New York, Melbourne, 1985. Second one, A. Butts. This particular book is a lot of problems, and you should see, if you want to go more problem, this is metallurgical problems. Metallurgical problems, McGraw-Hill. McGraw-Hill Book Company. New York and London, 1943. Now, this book is a very good compilation of very good problems in various areas of metallurgy. Third book, which you can also see, that is also again a good book, H. Allen Fine, and Gordon H. Geiger. A book name, Handbook on material and energy balance. This is 1979. published by Met Society of AIME. So, you should also go through these references for further reading.